Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
The Aurelia Institute is a nonprofit organization based in Cambridge, Massachusetts, dedicated to advancing humanity's future in space through research, education, and policy development. Their mission focuses on creating scalable space habitats, fostering public engagement with space exploration, and addressing the ethical and societal implications of life beyond Earth. The TESSERAE Project is a modular, self-assembling space architecture system designed to autonomously construct habitats in microgravity environments. These structures aim to support human life, scientific research, and other activities in low Earth orbit. The Institute also offers the Aurelia Academy, an educational platform offering courses, flight experiences, and community-building initiatives to train the next generation of space professionals, as well as policy and ethics initiatives and spin-out ventures for up-and-coming space companies. My guest on this edition of the Ex Terra Podcast is Evan Hilgemann, Senior Mechatronics Engineer at the Aurelia Institute. And Evan, welcome to the program.
Morning, Tom. It's great to be here.
Let's start a little bit about you. What the heck is a mechatronics engineer?
Yeah, that's a great question. It's sort of what it sounds like. It's a combination of mechanical engineering, electronics, and mechanisms. So a lot of things that are moving. You think of like a motor-driven hinge mechanism. Kind of bringing all those disparate fields together into one job role. My background in particular is a bit more on the mechanical side. My undergraduate degree is in mechanical engineering. I spent a number of years at JPL, the NASA Center in Southern California, doing mechanical engineering, but also expanded a bit into mechanisms. I was doing Mars rover operations for a number of years, so really I learned a lot of that robotics background and the mechanism side of things too. And now at Aurelia, I'm kind of bringing all that together to do a lot of our structural mechanisms and a bit of electronics and sensing work as well.
So let's talk about what inspired the creation of the Aurelia Institute, and then how does that differentiate itself within the space commerce industry?
Yeah, so Aurelia Institute was founded by Ariel Ekblaw, who's our CEO and founder. It's a spin-off of her PhD work from MIT. The TESSERAE Project was originally started as her PhD work. But we were spun off as essentially a nonprofit R&D organization. And I think that's what really separates us from other organizations in the aerospace industry, is that nonprofit status. We're very much a mission-driven organization. And we focus on scaling space-based infrastructure for the public good and generally trying to make a life in space, a life worth living. We're not trying to necessarily directly sell a product. We're trying to promote a particular vision for space. And that nonprofit status really allows us to do that, to be a mission-focused organization as opposed to be overly focused on, selling and producing and selling the product.
So if you're not selling a product, then how does the TESSERAE Project aim to change space habitat construction? Mm-hmm. And what are its potential applications in the commercial space sector?
Yeah, so to give a little bit more background on that TESSERAE project,
Sure.
As you mentioned in the introduction, it's a self-assembling system to basically form large structures in space. So one of the limitations you have now is your space station modules are typically limited by the size of a rocket fairing. TESSERAE is essentially a bunch of tiles that are hexagon and pentagon shape and kind of a baseline configuration that can be assembled once in space to form a much larger volume than what could be launched monolithically on a launch vehicle. And to get back to your question, as far as how are we using this to kind of change the way space is done, we see ourselves as kind of a technology incubator, a group that's developing technology and then working with other larger organizations in the business to really bring that vision to fruition. So we're kind of developing the technology, and then we're working with other players in the space industry to scale it up, to get that technology out there to where it's at a point where people can be using it, and eventually people can be, it can be implemented in space, and it's a place that people can live in. We also, that's kind of the base of the technology side of things. I'm very much on the technology side myself, but we do have a very active architecture and design side of the organization as well. So beyond just trying to develop this base technology and push it for adoption within the industry, we try and think about how humans are actually going to interact with this technology.
Right.
So yeah, thinking about how, we're in a world now where it's not just professional astronauts that are going to space. There are going to be more and more people like you and me, Tom, who maybe have opportunities to go to space and spend time there. And we want to make sure that the environment that people are being received into in space is something that's comfortable. A comfortable place that's made for humans.
I guess the best example of that is the probable next administrator of NASA. Jared Isaacman is one of those people. He's not a NASA astronaut, but he's been to space twice and actually done an EVA. So that really kind of does almost prove your point.
Yeah. So that's kind of where you're seeing some of the space commercialization start. But we definitely see a vision where access to space is much broader, even than just, an occasional private mission, where, it's something where maybe you're actually a scientist who's commuting to work for a month or two in space, and you're living in a lab that also has accommodations for people. And then eventually, even much further beyond that, space can become a tourist destination which is accessible to a normal person in the same way that aircraft travel is currently accessible to most people in a way that maybe it wasn't 50, 80, 100 years ago.
Where did the thought come from to build the habitat, actually build it in space? And I'm just reminded of something that I read not too long ago, where people that were kind of commenting on Star Trek of all things, saying how could that ship be so big and be built on Earth? And everyone knows there's space docks, and that it didn't build the Enterprise on Earth; they built it in space. Is that kind of? I mean, it's almost like life imitating art when it gets to that point.
That's one way to think of it. Certainly, it's hard to launch something as large as a Star Trek scale starship from Earth, and that's very much the vision that we have. Is we want to create infrastructure in space that people can use. So TESSERAE is certainly part of that, where you still have to launch these individual tiles up. But once they're in space, they can form space station. They're reusable, they're replaceable, and they can be used to form much larger structures, as you alluded to, than just what you can fit in that launch fairing. So to form those very large spaces in orbit, you have to go to some sort of on-orbit assembly or construction. It's not something that you can just launch from the ground, even with very large rockets.
Now, you mentioned that it's an autonomous construction. So what role do you anticipate things like AI and machine learning playing in actually making that construction happen? Because obviously you're not going to have people up there with welding torches putting it together.
Yeah, that's not the vision. That there are various technology projects that do look at welding in space and how do you do maybe more traditional construction methods in space. We have very much a system that does self-assembly in space. So essentially you have these tiles, they're released from a rocket. They need some way to kind of be kept in proximity to each other, either with a large enclosure or bladder, something like that, or with their own propulsion or other methods. But essentially, it's a semi-stochastic self-assembly process. So what that means is that you essentially have tiles that are moving around relative to each other in kind of a random pattern. They all have magnets along the faces. So you imagine hexagons and pentagons on each one of those sides. There's a pair of magnets. And those magnets can be actuated. So we have what are called electroactive magnets. That essentially means that we can, by sending electricity to a coil around those magnets, we can flip the polarity of them. That gives us the ability to do repelling. So essentially what's happening, that these tiles are floating around, the magnets are interacting, and if they come together, they can form a good bond, a good bond, which essentially is the shape that's desired. That's what we want. There are other ways they can come together that maybe we don't want, in which case they can actuate those electropermanent magnets and then separate, add energy into the system. And through doing that over and over in time, you eventually can build up a large organized structure. So that's beneficial to us because it means that there's no astronaut involvement in this whole assembly process. You don't need an EVA, you don't need a spacewalk. You don't necessarily even need any high-level intelligence overseeing the system. Each tile has its own intelligence, so it has aspects of swarm system involved, where each tile is kind of following its own simple rules. It's sensing its environment to understand what's around it, what other tiles it's connected to, and whether that's a desired state to be in or not, and then acting based on that. And then from that, you're getting an intelligent system kind of evolving from this set of simple rules that the tiles are following. As far as like AI and machine learning, it's not something we've implemented yet. On a larger scale, that certainly can come into play, especially when we're trying to figure out like what is the right algorithm we're going to use for these tiles to follow. What are the right sensing thresholds that we need to use, and trying to kind of set these basic parameters. But yeah, certainly the tiles on the like individual unit level need to have a certain amount of intelligence to do their job.
So then how does it become a pressure vessel? And how do you get oxygen into that pressure vessel? And obviously it has to be tested before you can put somebody inside. Yeah,
testing is an interesting question. We've done some analysis of full-scale systems to kind of convince ourselves that this is not just a toy. This is something that could be built at human scale,
sure,
and be usable for a space station. The magnets themselves would be used for that assembly process, and then to hold the pressure inside, you would need some sort of secondary clamping system to pull the tiles nice and snug to each other, clamp down, and hold that pressure in. This is similar in nature to some ways of how the International Space Station is assembled. They have individual modules. They're much larger. They take a lot of work and astronaut labor to put together. But then they essentially have a screw mechanism that pulls the two modules tight together to form that atmospheric seal. They bring it up to pressure, equalize pressure slowly. They make sure there aren't any leaks. And then it's at that point declared safe for human habitation. So you can imagine something similar to our case where we're forming this airtight system. You would, of course, need to introduce air into that system. So there's a process of outfitting that would need to happen, which is, again, something that would happen with the International Space Station, where you bring whatever equipment you can't send up with the tiles,
sure,
into that system and outfit it for human occupation. And part of that, in our case, would be introducing an atmospheric environment, making sure those seals are holding, and making sure it's safe for human habitation.
I know I'm kind of getting into the weeds on this, but
yeah.
I think about some of the inflatable habitats that are being produced right now, and they do what are called burst tests, and see how far they can overinflate it before it pops. And you can't do that when you're building it in orbit and waste that particular asset that you've already placed in orbit. So, I mean, kind of what are your parameters for making sure that it's safe for human habitation?
Yeah, I mean, there are various ways you can approach that question, and I'm not going to claim that we have a final answer to that today.
Sure.
But you can definitely do like sub-assembly testing on the ground. So, we have a good idea through analysis what sort of loading you're going to expect. We can't test the full system, but we can qualify that, hey, one edge is sealing appropriately, under loading that we would expect. And you can test that and you can qualify that. And this is something that's done all over the aerospace industry, where you have hardware that goes through very rigorous qualification testing. That's not necessarily your flight hardware, but you're using that to qualify your design and verify that the actual flight hardware is going to work the way you expect. And then there's some other testing that happens on the flight hardware as well. So there's that aspect of it as well. And then, again, much like other modular space stations, there is an assembly step that has to happen in orbit, and you have to be able to verify that assembly step is completed appropriately and is holding in your environment. So I think it's a combination of on-the-ground testing plus functional testing and verification in orbit that would make us confident that the system could keep humans alive.
Let's shift gears a little bit and talk a little bit about the Aurelia Academy. Can you talk a little bit about some of those programs and how they prepare individuals for careers in space exploration?
Yeah, absolutely. So the Aurelia Institute as a whole kind of has three primary pillars that we work out of. There's the architecture and R&D side, which is what we've talked about mostly so far regarding this TESSERAE system, thinking about how humans inhabit spaces in space, because it's a very different environment than Earth. That's kind of the area that I'm focused in. There's also a space policy pillar, and the one you're referencing is the education and outreach pillar of our organization. The primary program within that pillar right now is what we call the Horizon program. This is essentially like a semester-long program for students. The end goal of the program is to basically take them on a microgravity flight. So if you're familiar with parabolic flight opportunities, there's a company that will take people up in an aircraft that's specifically outfitted for this purpose, fly up and down, sort of like a roller coaster. And when you're going over the top of that arc, you essentially simulate microgravity for something like 20 seconds. So it's a very common way of getting a short-term microgravity exposure, without leaving the atmosphere, and is used very frequently by NASA and other organizations to test out hardware.
What is sometimes affectionately called the vomit comet.
It is affectionately called that. Yeah. Yes, you do want to take the motion sickness medication before getting on that plane. And most people, the majority of people, actually don't have issues. But yeah, it is a risk of being on that airplane. But yeah, it's a wonderful opportunity, both for us as a technology organization, for organizations like NASA and other players in the world to test hardware in the zero gravity environment. But it's also a fantastic tool for teaching students about what microgravity is, how things behave in microgravity, the problems that you have to address in a microgravity environment that you don't necessarily have to address on Earth. So we'll essentially take anywhere from 15, 20, 25 students. The numbers specifically vary year by year. We take them through a design build course. It's roughly a semester long, 15 weeks or so. They essentially come in and they propose their own project that they want to do in a microgravity environment on the parabolic flight. We then teach them the skills they need to build that. So they're students from all different backgrounds, both engineers like myself, but also designers, occasionally artists as well, who have an idea of something they want to test out in that microgravity environment. We work with them to then bring that to fruition, kind of teach them what they need to be thinking about to make their experiment work in microgravity, make sure that they're meeting all the requirements they need to, all the safety requirements and whatnot to actually install their experiment on the plane. We're providing a lot of experience and know-how to the students. And then at the end of that 15 weeks, we actually take them on a microgravity flight and they get to perform their experiment on that parabolic flight in microgravity. I think doing that full process end to end, there was actually something I was able to do through a NASA program as an undergrad. And it's just a very informative, project, and really teaches students about what space is, how people, how both people and equipment operate in that space environment. And it's really helping bring people into, get comfortable with the rigors that you need to design hardware for space. So that's kind of our main offering as part of Academy right now, but we kind of use Academy as a catch-all for other outreach and education efforts we envision doing in the future.
I want to talk about the policy piece of it in just a moment, but right now my guest is Evan Hilgemann, Senior Mechatronics Engineer at the Aurelia Institute. Take a moment right now to click subscribe so to be sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. And please consider becoming a paid subscriber. Whether you're a space professional or an enthusiast, paid subscribers have first access to premium articles and podcasts focused on the new space economy. Just visit www.xterrajsc.com and help keep the Journal of Space Commerce independent as we chronicle, cajole, and when necessary, critique the commercial space industry. Let's talk a little bit about that policy piece, Evan. What role does the Aurelia Institute play in helping to shape space policy and some of these ethical considerations that we have for future space societies?
Yeah. So first off, I'm going to give a little disclaimer that policy is not my area of focus. I'm very much an engineer and technologist, but I can talk in kind of broad swipes about the policy arm of things. Essentially, that's part of trying to make, life in space, life worth living, like I talked about before, that there are, certain things from the architecture and engineering side you need to think of. You also need to consider the environment that people are going to be living in. We need to make sure that we're protecting the space commons as a shared resource. And Aurelia wants to be part of that discussion and leading what we hope will eventually become more of a spacefaring civilization than what we currently have now. So within Aurelia, we focus a lot on ethics of technology and design. So that kind of goes into that architecture and R&D realm, where we're trying to think of what does this interior habitat look like in the microgravity environment to make it comfortable for a wide range of people, both people who are professional scientists or whatever who might be using the environment, but also visitors, also people who have maybe mobility constraints on Earth, which is less of a mobility constraight in orbit. You don't have gravity. And trying to think through that end to end of how do you make this a space. How do you make your space in space accessible to as many people as you can?
Sure.
And there's also a governance and human rights aspect to that as well, or to the policy arm. Where we want to make sure that policies are being put in space are really protecting the space commons. So that whole question of like, how are we balancing short-term desires for missions, for building things in space with long-term goals and long-term sustainability. As far as things that Aurelia has been involved in on the policy front, our CEO, Ariel Ekblad, is a technology and geopolitics fellow at Harvard Belford Center, so there's some influence there. We occasionally bring on space policy fellows to help with their organization and also run workshops at places like MIT, various conferences to get people thinking about these topics and how various space policy considerations are affecting our future in space.
Evan, what are some of the key technological advancements that have been developed by Aurelia? I know you've talked about your habitat construction, but I know there's a lot of things that go into making all that work. And how do they address some of the current challenges in space habitation?
Yeah. So I think is kind of a broad goal. What we're very much interested in technology is that scalable space architecture, or scalable space infrastructure, if you will. So that idea that we want infrastructure in orbit that we can use, that will be useful in the future, that can be repurposed. And all those things that we kind of take for granted with infrastructure on Earth, we want to build that in the space environment as well. On the technology side, we're focused largely on that TESSERAE technology now. So a self-assembling system of tiles. Within that, you have various technology, thrusts, if you will, from the actuation of those magnets, from your command and control strategy, and all sorts of little things that come up when you're trying to build a new autonomous robotic system. And then we do have interest in other areas as well at Aurelia Institute as far as other technologies that we're interested in pursuing and are trying to push forward. One thing that's come up multiple times is the what's called ECLIS in the space acronym environment, or essentially the environmental control and life support systems. Right now you have astronauts who are breathing, they have to breathe air, they have to drink water.
Sure.
And the International Space Station has a regenerative system for kind of keeping all those resources and available for astronauts in the proportion they need. We're very much interested in how do you make that system part of the environment in space through, say, like plant growth. Plants create oxygen, they can create food. They've also repeatedly been shown in space that astronauts like to have plants around. They're generally fun experiments to have. So we've looked a lot at how do you grow plants in space. There are experiments on the ISS pretty regularly looking at that, where it's one enclosed volume. But thinking through how do we then scale that up and make it really part of the living quarters and something that astronauts have around and are able to utilize more. So that's another technology area that we're interested in as well, is sort of that the environmental control and combining that with plant growth and other technologies to really enhance the well-being of astronauts in space.
So what obstacles has Aurelia encountered in its projects, and how have those been addressed?
Yeah. So again, I'm very much on the technical side. So a lot of the obstacles I come across are very much technical problems.
Sure.
We're building a first in the world system. So there's not a playbook necessarily for how to build this thing. And we run into those sorts of problems all the time. We're actually building up a small scale experiment right now that will get tested on the International Space Station, hopefully by early next year. But we're going to be doing the first like full 32 tile assembly in space to form a closed shell, again on a smaller scale than on the space station. So we're kind of having to address a lot of the details, that kind of come up when you're trying to build real hardware. I've touched on some of these before, but like, what is the right strength for those magnets compared to the weight of the tile? What is the right algorithm for these tiles to follow to make sure that you get the end state assembly that you need? And then going through all those little details. There are other operational constraints within the ISS and within space that you need to take into account. And then there's I guess going through all of those little details and kind of building that hardware for the first time is something that you certainly learn a lot about your system and learn a lot about the environment you're operating in by doing that. But I think that's a good thing to emphasize too at Aurelia is that like we are building real technology. We have the architecture and the R&D sides, and we very much like those two to be combined, where we don't just want like cool renderings of things that a cool, an interesting sci-fi space future could be without having real world engineering behind it. But we also want the real world engineering to reflect, a well-designed space that humans want to be in. So we're working kind of both those projects. They definitely work towards each other and overlap. We work both at the small scales to develop this technology and then also at large scales to prove that this technology can indeed be used to make a full-scale space station. And I think that a lot of the obstacles we come across are trying to just build up the base technology, but then also kind of bringing those disparate scales together and making sure that everything will work together in the end to get us a functional space habitat.
Outside of the academy, which you talked about involving some of the general public and going through that program, but how does Aurelia really involve the general public in some of these initiatives, and why is that engagement important?
Yeah, I mean, I think involving the general public is essential because we envision a future where the general public has access to space. And we want to make sure that we're taking people of all different backgrounds into account when designing these future spaces that they'll be able to inhabit. One of the primary ways we've been engaging the public over the last year or so is through an exhibition we have called the TESSERAE Pavilion. It's been at a few different places now. We had it set up here in Boston for a while. It was at the Seattle Museum of Flight for a while. It recently got taken to a TED conference in Vancouver, where hundreds, if not thousands of people have been able to explore this exhibition. And essentially what it is a roughly 1-to-1 scale mock-up of what we imagine a future space habitat could look like in a TESSERAE form factor. So it's a roughly 25-foot diameter dome that people can walk into. We have an aeroponics plant growth system set up in there. We have what is essentially like a window looking out with algae growing nearby and around it to utilize the sunlight that coming through that window, and also to generate oxygen for the crew. We have some other interesting design features in that exhibition to kind of teach people what a life in space could look like. I think it's very much sort of a design and architecture experiment, if you will. The spaces we have on space stations now, it's very much like it's the International Space Station is essentially a science lab, and it's outfitted primarily for that purpose. Again, we're trying to envision a future that's more where space habitats are built for normal people. And this is kind of that pavilion exhibition is one way that people can explore that vision, that they can offer us feedback about that vision. So we get great feedback from what we've put out there is people are confused by this or interested in that or think that this is a really good idea. And we, use that when we're thinking forward long-term about how we want these designs to evolve. And then there's beyond that kind of your typical education outreach. There's interviews, there's talks at schools, where we're trying to get people to think differently about what their future in space could be like.
When you talk to people as they view that exhibit, I'm sure you're aware that a couple of years ago, Inmarsat did a study that was a really high sample rate. They talked to over 20,000 people worldwide to try to get their impression of what space means to them, people in the general public, and generally people when they talked about space, they thought about, aliens or Star Trek or something of that nature. Do you find that when people go through that exhibit, they get a better handle on how the commercial space industry affects their everyday lives?
Yeah, I certainly like to think so, and especially thinking through like what the future of their life and what their, I guess, life could be like if they ever get to visit space. I can't say I'm familiar with that particular study that you referenced, but yeah, that's the vision that we're definitely trying to communicate to them. Is we have lots of people right now in the industry working on building space habitats that are going to be accessible by the general public that are coming through just our instance, this mock-up that we have, this exhibition. And we definitely want them to understand the value of investing in that future now, so we have access to the wonderful resources that low Earth orbit and the zero gravity environment offer in the future.
Just one thing more, Evan. What are some of the key takeaways that have emerged from Aurelia's journey, and how do they inform future endeavors for the company?
Yeah, that's a great question. I think it's from my personal perspective, like I come at this, my background was all in robotic space exploration. Again, I was working at NASA JPL. I did work on rovers and things like that. So I've never had to take into account people when designing space hardware. And it's a very different problem when you're trying to take people with you. And I think from a personal perspective, it's been very enlightening to see how much interest people have taken in just the ideas we put out there, in the exhibition that we have, in the future that we're trying to envision for exploration of space. And I think that's something that really motivates me personally, and something that I certainly take forward as we're trying to develop this technology. And I think it's very much reflective of Aurelia Institute's, reflective of our mission, of our desire for a future in space.
Well, Evan, it's been a fascinating conversation. I really appreciate you taking time to talk to us today on the Ex Terra Podcast.
Yeah, thank you very much, Tom. It's been great.
Evan Hilgemann is Senior Mechatronics Engineer at the Aurelia Institute. And that's going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, Audible, and many other popular podcasting platforms. Be sure to click subscribe so you don't miss any of our podcasts or any of our other videos. You can get daily updates on space commerce by subscribing to the Journal of Space Commerce on Substack at www.xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on X at xterrajsc. And please consider becoming a paid subscriber. Whether you're a space professional or enthusiast, paid subscribers have first access to premium articles and podcasts focused on the new space economy. Just visit xterrajsc.com and help keep the Journal of Space Commerce independent as we chronicle, cajole, and, when necessary, critique the commercial space industry. I'm Tom Patton. Thanks for joining us.
I wanna go faster, faster. Hands in the air, we're gonna crash. Searching for the answers, like Galileo. The proof is looking glass. Thirst for reason. Our dreamer's eyes we gaze into a sense of purpose, know my view. Like finding one